Hi everyone, welcome to the finale of our series on conversations with an astrophysicist about the cosmic microwave background. So we've had 2 episodes so far. We're finishing up this topic on polarization and the bicep results. And with me, as always, is the fantastic Dr. Katie Mack from University of Melbourne, Australia. How are you doing tonight, Katie?
Hello. Good, how are you doing?
I'm tired. It's been a long, sad day, and I know that we're going to hit on this a little bit too. But um, do you want to talk about it, or should I?
About little Philae.
Yeah, let's talk about Philae for a second before we get it. I think it's appropriate.
Yeah. Okay. Well, I mean, I think it's. I don't think it's a. I think it's a sad day, but it's not. It's not that sad. I mean, Philae has done an amazing job, and we should be happy about that. So why don't you give us the summary?
So so Rosetta, which we launched 10 years ago, has arrived at the comet P67. I can't pronounce it. 67P. Yeah.
67P
something. Apologies, we cannot pronounce those names. But arrived, and Philae, the lander, successfully separated from Rosetta and landed on the comet. Now, the landing itself was not exactly what they wanted to, but they landed, and Philae did have a.
So I want to just.
Go ahead.
I just want to point out, the landing was actually fantastically successful in the sense that they dropped the thing from the orbiter, and it fell for 7 hours, and it landed within 15 centimeters of their target landing zone that they picked out, which was like a nice, smooth, flat area. However,
right.
It was supposed to have harpoons that could like dig into the surface of the comet and little screws on its feet to hold on to the ice, and that didn't happen, so it bounced. Right. And apparently it bounced, and it was in the air for, not air, it was in space for 2 hours.
Yeah.
Because there's so little gravity on the comet that it like floated for 2 hours and ended up a kilometer away in a corner with really bad lighting, and so now it can't charge its solar cells anymore.
Right. That's the biggest thing. It's not that it didn't stick the landing. That's not the big deal. It's not like anything was technically broken or anything like that. It's the fact that it's stuck in a place where very little light will reach it, and it's powered by solar radiation. And so since it's not receiving a lot of light, it's not able to recharge. However, it has done a phenomenal job. It has done so much science and has made sure to send back all the data back to Rosetta, to send it back home to Earth. So with everything, with as sad as I've been, especially with their Twitter account, because oh man, it got a bunch of us right in the feels. But with the bad news that that it's not getting enough power, it did a phenomenal job scientifically. It did its scientific goals for that first charge, and it sent it all back. And it's not impossible that it will come back. It's not impossible. It's not going to be able to charge as quickly or as efficiently as ESA wanted it to.
Yeah. But it's getting closer to the sun, and it'll get more light, and maybe it'll charge up in a few months.
Yes. And I know that you wrote something up on Facebook earlier today?
Yeah. On my Facebook page, yeah. And we'll talk about where to find that at the end, I guess. But
so, actually, we can go into that a little bit right now, too, because we want to let people know how to interact with us. We see that we are getting some viewers in. Paul Stewart on the Q&A app says, good evening. So, good evening, Paul Stewart, one of our awesome people from New Zealand. So the way that you can get a hold of us is right here on YouTube and Google Plus is on the bottom left. There is a Q&A app, and so you can click that. It'll open up into a new platform. You can ask us questions where we can timestamp them as we're replying. You can also leave comments either on the Google Plus event, which I have open up on my second monitor here, or on YouTube. And I will be looking at Twitter as well. So I'm down here at Scientific Scott. And Katie is also on Twitter, the most followed astronomer in Australia, at Astro Katie. So, and then also we're on Facebook as well. There's KnowTheCosmos on Facebook, so I do have that event up there. And you are facebook.com/AstroKatie?
Mm-hmm.
Yep. So, and that's where you can find that article that you just did today on Philae. So, as much as I would love really to talk about Philae all night, we do have to finish up our series on the cosmic microwave background. So, let's start by doing a quick, let's catch people up for those that have not been able to see the first 2 episodes, and then we'll wrap up today. So, what's this cosmic microwave background? Let's get the Reader's Digest 2-minute elevator talk. Ready, go. Ready, go.
Okay, so the cosmic microwave background is the afterglow of the Big Bang. So in the early universe, the universe was hot and dense and smaller than it is now. And because it was so hot, it was radiating that heat as radiation. And that radiation has been traveling through the universe ever since then. And some of it is reaching us just now from distant parts of the universe, because as you look farther away, you're looking farther back in time, and so we can look so far away that we're looking back to that fireball state of the early universe. And so we see that glow, and we see it in every direction in the sky, and when we look at that glow from that early radiation from the Big Bang, we can learn about what the universe was like 380,000 years after the Big Bang. I mean, right now it's about 13.8 billion years after the Big Bang, and that was just right at the beginning, just within the first half a billion years. So it's very exciting. First half a million years, actually.
Right.
So it's very cool to be able to see this, and
so this is
it's
what we're talking about
some of the
right
best evidence we have for the Big Bang. Yeah, and so this is what it looks like. So this is a projection of the cosmic microwave background. So that this is showing the whole sky. The center of that picture is the center of the Milky Way, and the Milky Way galaxy, our galaxy, kind of stretches out along the horizontal. And so what you see there are little tiny fluctuations in the temperature of that radiation coming to us, and those correspond to little tiny fluctuations in the density of the gas at that time. So in that time, during this primordial fireball stage, there were little parts of the universe that were a little bit more dense than other parts. And when I say a little bit, I mean 1 part in 100,000. So just a tiny, tiny fluctuation in density.
I mean, we're looking at this, like, I know it's really easy to take a look at that and be like, oh, the Doppler radar system on my local news, and we see that the color shifts are drastic between blue and red, but we're talking about tiny, tiny, tiny fractions of a degree Kelvin. We're not talking about the difference between Florida and Michigan on your local weather map. Yeah. We're talking about tiny fractions of temperature there.
Right. So we can get the temperature of different parts of the cosmic microwave background, but one of the other things we can get from looking at the cosmic microwave background is the polarization. So polarization is sort of the direction of travel of a light wave. So a light wave has the direction that the light wave is going, but it also has like an orientation of the fluctuation in the electromagnetic field. Do you have the picture of that?
Yep, pulling up right now. So we're talking about this fluctuation. This is what we're talking about here with the electric field and the magnetic field.
Yeah, so this is an electromagnetic wave, a light wave that's traveling in the direction of the arrow, and the electric field is oscillating in one direction, and the magnetic field is oscillating in the other direction. So a light wave is a fluctuation in the electromagnetic field, and those fluctuations have directions that line up. And so you can use that to figure out kind of how the light is produced. And we use this polarization of light all the time. If you have a pair of sunglasses that are polarized sunglasses, then what they do is they block a horizontal polarization of light. And the reason for that is that, let's say you're driving and the sun is glinting off the car in front of you. The sun is probably going to be glinting off a horizontal part of the car in front of you.
Right.
And so it'll be, when it bounces off, it gets polarized horizontally. So those light waves then are sort of lined up this way, and the sunglasses can block that polarization. They basically have a little grating that looks like this inside of them. Sorry, it looks like this. And so anything that's vibrating this way can't get through. And so when you're wearing polarized sunglasses, you block a certain polarization for whatever you look at, and you can actually see it really clearly if you wear sunglasses and you look at a computer screen.
Because you're a cool hacker or something.
Yeah. So in some orientations, the light goes through really well, and then in other orientations, it gets blocked completely.
Yeah.
And that's because of the polarization of the sunglasses, and the light coming from the computer screen is also polarized. So yeah, so we use that in astronomy actually. We can use that to see how light is produced in astronomical processes, and I believe you have a cool picture of that as well.
A very cool picture of this. When you showed this to me earlier, I was like, what? So please explain what's going on here, because this is amazing.
Yeah.
This is so cool.
Well, yeah, so this is a simulation, but it's a simulation of something that you could totally do. And what they're doing is they're looking at the polarization of light coming off of the stuff swirling into a black hole. And basically, because the disk of matter swirling into the black hole is like really planar, it's a disk, it's a flat disk. Mm-hmm. The light gets polarized in the sort of orientation of the disk, but the light gets bent around the black hole, and so the polarization vectors kind of curve around. So those lines are showing which direction the light is polarized at any given point in the picture, and those get bent around by the fact that the black hole is warping space-time. And if you've seen the movie Interstellar, there is a black hole in that movie, and you can see that warping of space-time and how the...
La 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 la.
Okay, well, there is a black hole in the movie.
Yes.
It's on all the posters. There's a black hole in the movie, and you can see the disk being warped by... you can see the light coming from the disk being warped by going around the black hole.
Right.
Anyway, that's not a spoiler. That's the movie poster.
No, it's I'm on Twitter enough to know basically what's going on in that movie. Because I guess the downside of loving sci-fi and also having a lot of academic friends or friends in academia is that whenever there's any sort of quandary with the science in a movie, it gets lashed out. So I will see it one day.
So that we can argue about it.
What's that?
It's very interesting. You should watch the movie so we can argue about it because it's very interesting.
I doubt I'd argue with you. I would never argue with you. I would lose. I just know I would. So I will just you said something, I'm going to agree with you now because you are far smarter than I am. But yes, so back to polarization. First of all, I think your example there on showing the and actually it ties into movies too. We're looking earlier about 3D glasses. That if you go into a movie and you have, instead of like the red and blue ones, having the tinted ones that look, just like you have regular glasses on, they're actually polarized because of the way that the movie's being projected onto the screen bounce back at you, and you're able to see things in 3D. And the same thing goes here with the light going through the sunglasses. And we're able to see that the light's being polarized in the simulation of a black hole, which is so cool. But what does that have to do with the cosmic microwave background? What's that have to do with anything?
So in the early universe, there's light, there's like hot spots and cold spots, dense parts and less dense parts, and there's photons bouncing around and electrons bouncing around. And what happens is that if, depending on how the hot spots and the cold spots are like oriented during this time when the light is finally coming from this primordial fireball, it gives a polarization to the light. So we have an animation of that, which is a little bit hard to explain, but I will show you. So you take light that doesn't have a polarization. You have just as much light sort of going in this direction as in this direction, and that's coming from one side of space. And then you have some light coming from another side of space where it's just as much light going in this direction as this direction, and that's coming sort of this way. And so both of those bits of light bounce off an electron and get scattered in such a way that it sort of gets a polarization from that scattering. And it would take a while to explain exactly why that happens, but basically you have more light on one side and a little less light on the other side, and when they come together and both scatter off this electron, you end up with the light wave sort of polarized a little bit more in one direction than the other. And so when you look at the map of the cosmic ray background radiation, you can see that polarization. And then what that polarization tells you is sort of how the hot and cold spots are oriented in that sort of surface of the edge of the fireball, basically. And so you have these sort of polarizations. You can draw these like polarization vectors all along this map and see how there's sort of the light lines up in this direction one place and in this direction another place. And so there are two kinds of polarization patterns. There's so-called E-mode polarization and so-called B-mode polarization. And E-mode polarization is where you have like a hot spot or a cold spot, and you have the polarization all lining up like radially or tangentially. So in the E-mode polarization, you have either sort of like a starburst shape or a sort of circle shape of the polarization like lines.
Right.
And then in the B-mode case, you get these like pinwheels. And those are just two kinds of polarization. And you can take a map that has has polarization vectors drawn on it. You can have all these lines for, in this part of the map the polarization is over here, in this part of the map the polarization is over here, and you have sort of these complicated shapes. And I think we have a map of some polarization from the cosmic ray background, the little one.
Let me get that in here.
Yeah.
Put a lot of order.
Okay.
We'll pull it up. Here we go. If I can screen share, that would be beautiful. Here we are.
Okay. So this is a map of the cosmic ray background where you can see the polarization, and you can see that you have some of these red spots where there's a bunch of lines sort of lining up radially, sticking out of the red spot. Then you have other spots where it's more sort of lining up tangentially. You have some sort of colder spots where you have like a sort of circle pattern of the polarization, and then you have places where it looks like it kind of has some of these sort of pinwheels.
Right.
And so you can take that pattern and you can decompose it. You can take I only want to look at the patterns that have the E mode, and I only want to look at the patterns that have the B mode, and you can take the whole map and put it in sort of two pieces. One where you have only radial and tangential, and the other one where you have pinwheel shapes. So radial is where they're all sticking out like a starburst, and the tangential is where they're sort of circular. And so you can decompose that, and we have a picture of that too, I think.
Let's see. Here we go. Which I think is
so
awesome. I love this.
In this picture, so this is a picture where one side is pure E mode and the other side is pure B mode. So in the E mode side, you can see these pinwheel, the sort of starbursts and the circles, and on the B mode side, you can see the pinwheel kind of shapes. And the technical term for that is that the E mode is divergence free, and the B mode is divergence free. And we don't need to go into what that means, but basically, the curl, the sort of pinwheel thing, is only shows up in the B mode side, and doesn't show up in the E mode side. So those just like so basically, yeah.
So like when we're looking at this, because it looks honestly, if you're just looking at it, you can kind of see that if you overlap them, they'd be somewhat in the same area. But how were those taken apart? How were those separated? Does that make sense?
It's a complicated mathematical thing to how you separate them.
Lots of advanced math.
I can't really go into that really, but
okay.
It's you basically you take the part that has some curl and the part that has some divergence, and you separate those out. But it would take a lot to explain exactly how that goes, and it's not the kind of I haven't done that to a CMB map, so I can't go into the detail on that.
Then maybe I should ask, what's the purpose of splitting those up? Like, what do we get out of it when we do that?
Yeah. Well, the purpose is that certain kinds of processes in the early universe produce pure E mode, and certain kinds produce B modes. And basically, anything that has to do with just density differences gives you E mode. So I told you about, if you have a hot spot here and a cold spot here, and then the light comes and hits an electron and gets scattered, that gives you pure E mode. The kinds of things that can give you B mode polarization are things to do with gravitational waves and gravitational lensing, and that's intuitively that's because gravity does this thing where it stretches in one direction, it pushes in another direction. And so that can end up kind of tilting things around in a sort of curl kind of way. And it's actually really complicated to explain how that works. But the point is that things to do with gravitational waves and gravitational lensing can give you B modes. And so the big exciting thing about BICEP2, this instrument that said that they might have seen a signal from the Big Bang, was that they saw B modes. They saw B-type B-type polarization patterns in the cosmomicrowave background, and we have a picture of that too.
Yeah, right here.
And so you can see, just looking at this picture, this is the B mode part of the picture. So this is just the part with curl, and you can see the little sort of pinwheels going around those hot and cold spots in the picture. And so So when that was produced, it suggested that BICEP2, this instrument's a telescope at the South Pole, might have seen signatures of gravitational waves in the early universe. And these gravitational waves, if they were there and producing this pattern, would be like really important, because it would tell us something about the very, very, very first moments of the universe and what happened, and it would tell us something about quantum gravity, and it would tell us about, sort of seeing gravitational waves, which we've only seen indirectly in a couple other ways. So everybody got really, really excited because it looks like we'd seen gravitational radiation from the early universe, which would be super huge, and it would relate to the theory of inflation, and we might talk about that in a future episode, I guess.
Can we touch on that? I know we are going to talk about that more in a future episode. We've talked about that, but why would that be a big deal? I mean, like a quick. I know it's complicated, but why would because that's the biggest thing. I remember when this came out, I am not an astrophysicist. I am not. I love doing science communication, and I had to do a lot of research looking into this. But why is it a big deal if we're seeing these gravity fluctuations as opposed to anything else? What's its implications for inflationary theory or something like that?
So basically, we think that inflation, if it happened, produced gravitational waves. Now, inflation is a process by which, in the very early universe, the universe goes from it grows exponentially in an extremely short period of time. So this is going from going in the time before 10 to the minus 35 seconds. So a tiny, tiny, tiny fraction of a second in the very, very beginning, right?
So
when the universe was created, basically.
Right here. This is the time that we're talking about.
Yeah. Yeah. And so if that happened at that time, then inflation would produce fluctuations in the density of the matter. Fluctuations would actually be coming out of quantum fluctuations, and quantum fluctuations are like basically the uncertainty of the position of a tiny subatomic particle. That's a quantum fluctuation. Incredibly tiny processes. And those quantum fluctuations could be sort of grown into fluctuations in the density of matter on large scales. And this is what we think happened with inflation. And if that happened, then it would produce gravitational radiation, it would produce these gravitational waves. And if we saw a signature of those gravitational waves in the polarization of the CMB, then that would indicate that inflation happened. And we don't know for sure if it happened. There's reasons to think it should have happened, but we don't know for sure. And so this could have been proof exactly, but like evidence for inflation that would have been really, really compelling. Unfortunately,
so I wanted to share something real quick to go into why that might not be the case. So what are we looking at here? And then we'll go to the next slide that we have up here as well, as far as what they saw. Yeah. So what are we looking at here? This is a beautiful image that you shared with me earlier.
I love this image. So this is a picture of, it's basically a picture of the magnetic field in the galaxy. Now, so the short answer with why BICEP 2 might not have seen quantum gravitational waves in the polarization is they might have seen polarization from dust in our galaxy. Now, what happens, how that works is we live in a galaxy.
Yes.
And our galaxy has a lot of gas and dust. And in this projection of the sky, you see the galaxy is the sort of line across the center, the horizontal line, and the center of the galaxy is the center of that picture. And our galaxy has magnetic fields. And in those magnetic fields, the dust grains from just stardust basically, dust grains can get sort of lined up in the magnetic fields. What happens is that the dust grains are not perfectly spherical, they're a little bit elongated, and so they can kind of line up along field lines, and so you can have a whole bunch of dust grains lined up sort of parallel to each other in a line, and that traces out the magnetic field of our galaxy. Because the dust grains all line up, and then they get heated up by starlight and things like that, and they emit radiation, and when they emit that radiation is polarized along the axis of the dust grain. So if this is your dust grain, it's putting out radiation like in polarized, parallel to the orientation of the dust grain.
Right.
And so when you look at a polarization map of the whole sky, you can see that in the polarization map. And this is a map of the light coming from the galaxy. And you can see that it really traces out those magnetic fields because of that dust. And so the BICEP 2 people tried to estimate how much that would contaminate their picture of the sky and their picture of the polarization, and it looks like they underestimated how much the dust could contribute, because if you actually look at like the amount of polarization that the dust gives you, it can be enough to account for their whole signal. So all those beautiful little curly Q things could have been dust. So this is a picture from a blog post I wrote about the BICEP 2 result, where on the left-hand side, now we don't need to go into exactly what's being shown here, except it's basically the strength of the signal as a function of like scale,
right?
Like how big of a piece of the sky you're looking at. And on the left-hand side is the picture that is the plot that was in the BICEP paper, where they have those black dots with the lines. Those are their signal, and they show that the signal is way high above what they expect from dust, which is all those little lines lying flat along the bottom.
Mm-hmm.
So they have this bump, and they think it's way higher than the dust, and so it should be totally distinguishable. But then the Planck satellite went and looked at the dust at a different frequency, and they estimated how much signal you'd get just from the dust.
Right.
And in this picture, that bump that you see that's circled corresponds to the same place and the same magnitude as the bump that the Bicep 2 people saw. And so basically what Planck said is that that whole signal could just be dust. All those dust models were too small. That signal could be entirely made of dust. So yeah, so Bicep 2 saw something. They saw polarization, but it could have been polarization due entirely to dust.
Now, but
just a bummer.
Which I remember it was a huge bummer when I remember it was huge news when it came out, and then almost immediately, I mean, my Twitter feed was just going back and forth about it.
Yeah.
And we're more, and I think I love what the Bicep team did is they went back and they looked at it and they had other people look at their data, which is the best part of the peer review process. Is let's get more eyes on this. Let's get more ideas of what this could be. And I know that there's aren't they still doing observations to try and redo their experiment to see if that's coming back?
Well, what they're doing is they're doing a new joint analysis with the Planck team, and that should help to distinguish how much of their signal could have been actually primordial and how much could have been dust. Right. And there's also a number of other experiments that are trying to measure the same thing, and hopefully they will also find they'll also find whether the signal is there or not. So, so it's still, the jury's still out whether we can see these quantum fluctuations, the gravitational waves in the early universe in the cosmos-microwave background. That's one of the most exciting things to look for because it would be such a huge result. And we thought that Bicep discovered it, but they didn't. It looks like they saw something, but they couldn't tell if it was just dust or the cosmos-microwave background. I mean, when you think about it, it's really difficult to tell what you're looking at with a cosmos-microwave background, because you're looking everything in the universe that you can see is between you and your signal, right? So like, you're looking through. So you're just looking through so much stuff.
Yeah, you're
literally everything.
Looking at the very first light that we're ever able to observe, and you have to look through everything to get to it. It's not like, oh, there's everything a lot of stuff. It's literally everything in that direction is between you and it.
Yeah. Right. Yeah, and you have to find some way to figure out what is, just a bit of dust in our galaxy and what is actually, billions of light years away at the moment of the first light in the universe.
Because why do something easy? Why? Let's.
But we can learn so much. We learn so much about the early universe.
That's exactly it. I mean, from the very beginning of our series, we're getting into just what is it? A fraction of the static we saw on our old TV is actually the light from right after the Big Bang, and we're getting baby photos of the beginning of our universe, and now we're still going further, trying to understand more and more and more, and closer and closer and closer to when the Big Bang happened. And so it's not something that is like, the Big Bang happened, we can see the first light of it, but we're not, there's still a little bit of time there where we don't know what's going on, and we're still trying to figure that out.
And there's so much information in that light. I mean, not just the patterns on the sky, but also the polarization. We want to get as much information out of that first light as possible because it tells us how everything began. Everything that we see in the universe today evolved out of little fluctuations in density that we can see in the cosmos-microwave background. So it's pretty cool. It's awesome.
It's really cool. I still can't wait and see what else we're able to get from it. I'm a huge fan of the early universe and how it has evolved to bring us to where we are today. I know that is something that you like playing with as well, and you'll research a little bit.
Yep. I've worked on some of these issues in my research also.
which is awesome. I mean, there's just so much out there that we're trying to figure out, and there's so much work that needs to be done in all fields of science, let alone astronomy, let alone cosmology, let alone early universe. I mean, there's so many different parts that we're still trying to figure out, and the most brilliant minds out there are trying to do it. So. I hope. I mean, I know tonight's or wherever you are in the world, it's a little hard to wrap your mind around on what these fluctuations are and the polarization and what it means. But what we're looking at is we're trying to understand that light and what caused that light to be seen the way that we're seeing it, and if there's something in the way that's causing us to see it being polarized or not. Because if it's polarized for a reason that's not dust, that's not something interfering with it, but if it's polarized because of gravity at this early stage, that has so many implications to the physics of the very early universe. That quantum gravity is something that we don't even know. We don't have a way of combining gravity with the other three forces yet. That's still something we haven't figured out. So if we can find ways of doing that would be awesome.
Yeah.
Is there anything you like to add before we go besides, Philae, we love you and we hope you wake up?
No, I think that's. I have a blog post about this topic about Bicep 2 and the gravitational waves. If you want to check that out, it's on my blog, which is called The Universe in Theory, and it's I think it's astrokatie.blogspot.com.
Yeah.
Something like that.
You pull that up.
It's linked from my webpage. My webpage is astrokatie.com, and you can find my blog there.
Pulling it up. Let's see here. Your blog. Here we go. The Universe in Theory?
Yeah.
So yes, here we go. So I will screen share this real quick. So this is what we're talking about from September?
Yeah. So that goes through a little bit of the history of that discovery and some new research that talks about what it might mean.
Yeah. So if you want, head over to astrokatie.com/writing. If you click on our blog, it will pull us up, and it is the latest article. So go ahead and check that out. I do want to thank everybody for retweeting and sharing out, and also for transitioning over from all the different places. I know that we started this over off at Space Fan News, and now we have our home at KnowTheCosmos, so I do really hope that everyone would please subscribe and like this as we continue to have more and more episodes. I don't know if we've come up with what we are doing in 2 weeks, but I know that we are doing an episode in 2 weeks.
We haven't. I guess we'll figure that out, but it'll be awesome. So you should totally come back.
It's also a good thing for all you, dear viewer. If you have anything that you would like to know about the universe, about astronomy and cosmology, I mean, we've already dug into dark matter and supernovae, gamma ray bursts, now the cosmic microwave background. If there's anything that you'd like to know, please let us know. Send a tweet to me at Scientific Scott, or also you can tweet at our page at KnowTheCosmos. And Katie is at AstroKatie. Send her some suggestions, but don't send her, hey, this is my theory of how the universe is. Will you vet it for me, please? Because that is not a cool thing to do to any academic ever. I know of way too many horror stories, and even I've received some. Like, I am not a PhD astronomer. I'm sorry, but I'm not. So just don't, be nice, and if you have a question, ask us, because a lot of times there's some really interesting information, not only in the direct answer, but the story around the answer. And we love being able to tell that story. So, again, thank you, everybody, for watching. Thank you, Katie, for being with me all the time, helping me help everybody know the cosmos and get to do some awesome stuff. I know we have come up with the official date that we will be releasing the, I guess, the renewal. I think we can officially announce it. So it's going to be Tuesday evening in North America and Wednesday in Australia, the reboot of Pint in the Sky, where Katie and Dr. Alan Duffy sit down at a local pub by Swinburne and have a pint and talk about astrophysics, cosmology, and the first one is about, you'll have to wait and find out. I'm not going to tell you what the first episode is about, but it's really funny. I loved editing it. So that will be up again Tuesday evening here in North America and Wednesday for the rest of the world. So that's over at the Castro YouTube channel, which is Astro Center. So if you youtube.com/user/Astro ASTROCENTRE, that is their YouTube channel. So go ahead and subscribe to them, and you will see them.
And there's a link to those videos on my webpage as well.
Yes, and there will be up on KnowTheCosmos too, as I get that updated and put live. And I'll put them down in the doobly-doo everywhere. So yeah, I'm rambling because I'm tired. So we're going to sign off now. Thank you all again, and we will see you all in 2 weeks. And yeah, see you later.
Bye.